So this is our second application, again, of our linear equation y prime, of our general form of y prime, some function of x, which could also be a constant, but it's not a function of y because it's multiplied by y, plus our forcing function, which could be a function of x or could be a constant. And in this application, we're going to deal with chemical mixing. So here, y is going to be the concentration as a function of time of a solute and x, our independent variable, is going to be time, t. So we're just going to swap out c in place of y and t in place of x. So imagine we have a bath of fluid. So we have a bath of fluid, and we are adding fluid with a flux Q. This is our flux of fluid we're adding, and the fluid has a concentration of our solute of C in. So we're adding fluid in with a concentration C in, and the concentration of the solute in the bath is going to change with time, and we're going to remove fluid from our bath with that concentration C, with the concentration equal to that of the fluid. So in this case, C could be concentration of salt, for example. If we're adding salt to our cooking, our soup or something, or it could be bacteria or pesticides, where our bath is a pond and it's being fed by a stream with pesticide-ridden water, and it's entering the pond and it's exiting through another stream. So there are a variety of applications. So let's define Q, and that is that's our flux, and that's in, let's say, meters cubed. So it's a volume flux, meters cubed of fluid per second. And our concentration is, let's say that's grams per meter cubed. So grams of solute per cubic meter of fluid. And again, C in is our input concentration. So our mass conservation equation is the rate change of mass of our solute is equal to the balance between what we're adding into our bath with the concentration of C in minus what we're removing from our bath with the concentration of C, which could vary as a function of time. So that we're adding mass through the top of our system here, and we're removing mass out the other side. This is our stream flowing out of our pond. And so so this is a differential equation involving mass and flux, but let's convert this mass, flux and concentration. Let's convert this mass to a concentration. So the the concentration as a function of time is equal to the mass per unit volume. And that's the volume of our bath here. So dm dt is equal to dc dt divided by the volume. And so if we plug this into our equation, we get dc dt is equal to, oh, actually I'm going to write my c's on the left hand side, so I'll bring this term over to the left hand side. So we have plus q as a function of t over v. C as a function of t is equal to q times c in. And this is our differential equation. This is our equation of our reference, our basic form of y prime plus p of x, right? So this is only dependent on the independent variable t, and we have y is equal to our forcing function. So again, c is y, and dc dt is y prime. So in our application, let's assume that the amount that we add and remove, amount of fluid flux that we add and remove, is equal to a constant. So we're just adding fluid. Our stream feeding our pond is feeding it at a constant rate, constant flux, and the stream removing water from our pond is removing it at the same constant rate. So here we have an equation of C prime plus our constant flux Q naught over V times C is equal to Q naught times our input concentration from our inflowing stream. And so this is our linear first order ODE. And when we solve that, we get the solution is an exponential function just as we've seen before, whether it be in our LC circuit or our mass on an inclined plane. So if let's sketch out the solution. I'll slide this up here to give myself a little more room. So if we sketch out our solution, we are going to get something. So this is time t, and this is our concentration. And we're going to start off with an initial concentration. This is our concentration at time is equal to 0. And just as we've seen before in our other solutions, we're going to reach a maximum concentration. Actually, the maximum concentration we're going to have at infinite time is equal to the concentration of our input fluid. So you can imagine that as we add this fluid from our inflowing stream, eventually we're going to replace all the pond water with this incoming fluid, and so the final concentration is going to equal Cn. And so we're going to get our concentration is going to rise initially rapidly at first, and eventually is going to level off at the concentration of the fluid entering our stream. Okay, well, I hope this makes intuitive sense. I guess the problem that I'm going to have you solve in the homework is to solve for this curve.